Ah, immortality. Previously only for the gods and individuals with a fetish for chopping each other's heads off. In more modern times, science is coming closer and closer to both identifying the tapestry of things that cause humans to grow old, and, slowly but surely, taking the first steps into finding ways to delay and even reverse this process for fun and profit. So, just what causes individuals of the human persuasion to grow old and die? Who was the oldest confirmed human? Are there any living things that are biologically immortal? And if there was an option to become biologically immortal, would you take it? As to that last question, surprisingly, according to a study done by the Pew Research Center, 56% of Americans wouldn't even take a treatment that would extend their likely lifespan even a few decades, and only 4% would say yes to a treatment that would allow them to live past 120. In slight contrast, a much less formal poll done by us showed that 61% of about 30,000 of you would take a pill that would allow you to become biologically immortal and locked into your prime age body. On both of these, as for those who responded no, they have no interest in biological immortality, we're going to make the argument that these people are all pathological liars, and virtually all of them actually would take such a pill were it a real option instead of a hypothetical one. And the real-world evidence is extremely clear on this point. More on this later, so stay tuned. Before we dive into that, who the oldest person in history was, and the fascinating mechanisms involved in growing old, if you're interested in learning about how the stuff we're going to talk about today applies to you and your specific DNA, today's sponsor, Adentro, has got you covered. And for free if you've ever used 23andMe, Ancestry, MyHeritage, and similar services, as you can simply download your raw DNA file from those services and use it on Adentro for a lot more analysis than those others provide. Or if you've never used one of those, you can order a DNA test kit for yourself or as a gift for someone. Which, if you're a data nerd like we here at Today I Found Out, you're gonna love this because it's super fascinating. For example, you can analyze factors that go into your longevity. On this, based on my DNA, it seems I'm predisposed to high antioxidant capacity and roughly average on telomere length. We'll get into what that's all about later in the video. But also, looking beyond, you can see your predisposition to various diseases and other health-related items, potential risk factors for you for various pharmaceuticals, and a ton more. What your genes say about your behavior habits is also super cool, and on mine, I particularly found that genetic predisposition to introversion results humorous. Checks out. Also, if knowing more about your ancestry is your thing, they've got you covered there too, even going back to ancient ancestry. For example, on mine, this is mostly West Eurasian, which, no surprise there, but the rest of the mix was interesting, as was the 2.82% Neanderthal DNA and 0.5% Denisovan DNA I'm sporting. So at some point, someone in my ancestry enjoyed them some interspecies lovin'. In any event, it's super cool if you love nerding out on stuff like this, or know someone who might and want to get it for them as a rather unique gift, and it's also potentially extremely practical when talking about what the health section reveals about your genetic makeup. They also update the results over time as new research is done, as well as link to the peer-reviewed studies right there for you to read up on everything yourself if you want for extra nerding out on it all. If this all sounds interesting to you, you can get 10% off one of their DNA kit packages and support our efforts on this channel at the same time by using the code TODAY at checkout. Or if you've already got your DNA file from Ancestry or similar services, again, you can see quite a bit about your DNA for free using that. Or if you want to upgrade to the ultra deep dive version of their service, you can get 10% off that with the order code TODAYRAW. Speaking of great genes, let's now talk about the oldest known human to ever live. On this one, outside of biblical figures like Methuselah, who it's claimed lived to 969,
Nice.
and Andrew Martin, one of the greatest humans to ever human and who lived to be exactly 200 while looking remarkably like Robin Williams, the oldest confirmed human ever was one Jeanne Calment of France, born on February 21st, 1875, and dying on August the 4th, 1997. For those who don't want to do the math, that means she lived 122 years and 164 days, an extremely significant figure as it turns out, because without awesome science fixing an issue with regards to how the human body works, that's always going to be the approximate upper limit for humans, and there is otherwise nothing you can do about it. Even if every other health issue is cured, you lived a perfectly healthy life and avoided the glowing orb in the sky, always watching, judging, basting us with its cancer rays in its attempt to destroy us all. Wear your sunscreen, my friends, or better yet, just stay inside. It's not just the sun that exists out of doors. There are literally people out there. Moving on from the oldest human, we'll get into potential biologically immortal creatures later in the bonus facts and why this is so hard to determine, including there being some creatures alive today that are over 10,000 years old. But right now, we're going to talk about one creature that isn't biologically immortal, but is often claimed to be on the interwebs, and what this has to do with why humans naturally cannot live for more than 120 years or so. The creature in question is the lobster. So why are they often claimed to be biologically immortal by people who are wrong and should now go sit in the corner and think about their life choices after spreading such misinformation? Well, to start, cells make up all living creatures on Earth, from humans to lobsters. Shocker, I know. However, cell replication is limited based on nucleotide sequences called telomeres, which are found at the ends of chromosomes. In a nutshell, telomeres prevent the strands of DNA from coming undone and also prevent them from accidentally fusing with neighboring chromosomes. The issue is that these end caps get shorter and shorter each time the cell divides, owing to the fact that the enzymes that duplicate the DNA, with a little help from a short piece of RNA, cannot do so all the way to the end of a chromosome. So something gets cut off every time a replication occurs. Thus, telomeres ensure that what is cut off isn't critical information. However, the results of this shortening each time is that telomeres eventually become too short to provide an adequate buffer. For reference, human cells can only be replicated around 40 to 60 times before the telomeres become too short. This leads to the cell no longer being able to correctly replicate itself and cell death. Thus, if you took every cell in your body at the time you were born and accounted for all the cells they would produce and so on, then multiplied that number by the average time it takes for those cells to die, you get what is known as the ultimate Hayflick limit, and in turn, the maximum number of years a human can theoretically live, which ends up being around 120 years. On top of this, outside of scenarios where there's a serial killer currently hiding in your home waiting to murder you when you fall asleep, little knowing that tonight's the night where this sleep becomes your eternal slumber, which is totally an illustrative hypothetical scenario and not definitely accurate to your present situation, how likely you are to die at any given moment of something is strongly correlated with telomeres length for various reasons we'll dive into more in a bit. As you might imagine from this, research into methods and substances that increase telomeres length in a healthy way is ongoing. Although it's not as simple as you might think, given a continually decreasing telomeres length comes with significant protection against cancer cells that cannot repair this as they divide. As to how most cancer cells that can kill you deal with this, they generally are associated with high telomerase, which is a natural enzyme that lengthens telomeres, allowing them to continue dividing until they kill their host. So ungrateful after all the nutrients and things you provided them. This all brings us back to lobster cells, which work a little differently. A lobster's body produces quantities of the enzyme telomerase even into adulthood. While as alluded to, humans and other vertebrates also produce telomerase, our bodies only usually produce it while in embryonic form. The result for the lobster is that the DNA in their cells can continue to replicate indefinitely, hence why it's often claimed that lobsters are technically biologically immortal. The problem here is that there is way more that goes into being biologically immortal and growing old than just telomeres length, and the lobster is susceptible to all these factors very similar to humans, and even some we aren't. For example, as Tematoa so aptly demonstrated, lobsters never stop growing. The problem for them is that, over time, part of the process of this growth in molting takes more and more energy as a lobster increases in size. And the amount of effort it takes for even a 30 to 50-year-old lobster to molt kills between 10 and 15% of the lobsters every year. Elderly lobsters have also been observed to stop molting altogether. This too will kill them eventually via being more susceptible to various diseases similar to elderly humans. So telomeres certainly is one factor in why humans can't currently live forever. But what about all the other aging factors that more or less play off each other in a sort of synergetic snowball effect of death? First, let's talk about more general DNA damage, as it highly correlates to aging and even premature aging. For reference here, in each cell, about 10,000 to 1 million molecular lesions, damage to things like your DNA, RNA, and proteins, occur every single day. And there are countless factors that cause such damage. From a practical standpoint, in terms of what we can control, this includes things like ultraviolet rays from the glowing orb in the sky bent on killing us all. This one is arguably one of the most visible ways we age. You see, while our skin does naturally produce less collagen once we reach adulthood and less each year, UV rays, coming mostly from the sun, unless you're using aging accelerator devices known as tanning beds, ultimately cause about 80% of the visible damage to our skin in the form of wrinkles and the like as you season. All once again showing why remaining in the basement and avoiding any and all human interaction and natural light is the proper way to live life.
Oh yeah, okay buddy.
In any event, other things that affect the level of damage you receive on a given day include things like diet, your propensity to get hammered with other humans on the weekend, smoking anything, and similarly, air pollution, which for a lot of city dwellers is a quite bad one, etc. All of these things can cause cellular and DNA damage. Another huge one is our largely collective insistence to never get consistent, proper sleep, as we've covered in our video, What's the Best Way to Get Good Sleep? In fact, good sleep habits are arguably the single biggest thing you can do to significantly extend your lifespan, as well as improve your quality of life during those years. If you haven't already, go check that video out after you're done with this one. It's one of our best and most practical we've ever done here. But going back to the whole 10,000 to 1 million molecular lesions per cell per day, while this might sound like a big number, it's actually very tiny next to things like the over 3 billion base pairs in your DNA. However, given that whole everyday thing and the fact that your DNA staying unchanged is kind of critical to the body bodying, it would very rapidly become an issue if unchecked. As you might imagine, given that most of us don't achieve the sweet release of eternal sleep until existing for about 28,000 days, your body does, in fact, check it, very literally constantly. And when it finds a problem, it does something about it, primarily in 3 different ways. First, by trying to repair the damage. Second, if it can't, it will trigger the cell to enter something called senescence, which means the cell will stop replicating. Or third, it will potentially go all nuclear on the cell, triggering cellular suicide. As to how such DNA repair mechanisms work, this is insanely complex, but in a very oversimplified nutshell, damage to DNA can usually be identified by certain enzymes and, once identified, to an extent anyway, can be repaired via utilizing the undamaged strand of DNA's data to complete the repair. And noteworthy in terms of longevity of life, one paper by Alex Freitas and Joao Pedro de Migajalis showed that individuals studied from 100 to 107 years old had markedly higher levels of certain DNA repair enzymes than is usual in adults from 20 to 70. Further, when looking at mammals in general, a given species' mechanism for repairing DNA correlates extremely strongly with natural lifespan. Now, if a repair can't be completed, as noted, this can in turn potentially trigger stopping cell replication, though again, none of these systems are perfect and DNA damage accumulation can occur over time which isn't stopped, and thus the cell will potentially happily replicate this. However, the vast majority of such mutations or damage to DNA will cause no discernible change in cell function, or it will simply result in a change that results in the cell death. So no laser eyes, mind control powers, or ability to manipulate magnetic fields for you, unfortunately. On this note of DNA damage and mutations largely either doing nothing or resulting in cell death in most cases, this is how certain cancer cell therapies work. Things like chemotherapy and radiotherapy attempt to cause so much DNA damage that the cell cannot repair it. And because most DNA damage unrepaired results in cell death, the cancer is killed. As to why this works so well on cancer, cells that more rapidly divide will be the first to succumb to such damage, which includes most cancer types. Unfortunately, other rapidly dividing cells are also going to be negatively impacted, which is a problem. But let's just say most people would rather take their chances and have those side effects than their cancer ultimately making it so they cease to be able to watch Star Trek: The Next Generation, Ted Lasso, and The Good Place. This all brings us around to the results of basically every poll that says most people wouldn't take a pill to allow them to be locked into being biologically immortal in prime body condition. As previously noted, we're hypothesizing that given that the vast majority of elderly people diagnosed with some form of cancer ultimately do choose to opt in for rather excruciating cancer treatment, that, for most, they'd change their no answer on this biological immortality pill question if they otherwise only had months to live if they didn't. And as for those who wouldn't change their answer, people, for example, who perhaps have a terminal illness but content to let it run its course rather than be treated, these mostly comprise very elderly individuals who at this stage have a body well past prime, featuring random constant aches and pains, perhaps chronic health conditions significantly negatively impacting quality of life, all the while watching friends and loved ones die, and for some, for various reasons, also having little purpose, all key factors for humans' happiness or not. This is all a trifecta of things that can reasonably cause you to think, yeah, I'm ready to go. Except we propose that even most of these individuals would take the pill precisely because that pill addresses these factors, which are generally cited by people who say they wouldn't. First, the pill would restore their body to prime of life condition and for many get rid of their chronic health issues in the process. Or even if not on a specific condition, it would give greater hope that science would soon figure it out, with all of these experts now with potentially hundreds of years of life to figure out how to cure an issue. And these individuals with a given condition now potentially have even thousands of years to live while awaiting such a cure. Or hey, with all that lifespan, maybe just devote your life at this point to figuring it out yourself. After all, you now have potentially all the time in the world to do it in, and one heck of a purpose, not just for yourself, but for all the people suffering from the same condition. Further, their loved ones would also likely take the pill, and as restoring the body to prime of life condition also gets rid of most of the late stage life health issues, outside of accidents and things, very few would be dying even for hundreds or even thousands of years potentially. And as for purpose, which is pretty key for mental health, if you had potentially infinite time to live, you could really think big on that one and explore fully just about everything life has to offer and do it all with prime of life mental capacity and energy levels. There is always more to learn in both knowledge and skills, careers and business ventures you haven't tried, and there are always other humans who need help. Further, given such lifespans and time to devote to learning and pursuing everything, we're just guessing humanity would advance insanely rapidly in countless ways, resulting in the world and worlds we'd reach with these advancements constantly changing and becoming ever more interesting, as well as allowing for interstellar travel in more practical human lifespans. Of course, there may come a time when one feels like they've done and experienced it all and are ready to be done. And in fact, we'd guess most would get there eventually. Just we are conjecturing that for most it would take vastly longer than 80 or so years to feel like they've reached that pinnacle. But once you did, the solution would be pretty simple in either ceasing to take the pill that makes you biologically immortal and letting nature run its course, or as few might be inclined to wait or go through such a biological decline, we're also hypothesizing that suicide, similar to Star Trek The Next Generation's Half-Life episode or The Good Place finale, would become accepted and common. In the end, probably accompanied with a slightly more cheery version of funerals, but in this case, where the person ceasing to be gets to be part of the party celebrating their potential thousands of years in the universe, accomplishing and experiencing all manner of things. Let us know your thoughts on all this in the comments below and whether you would take such a pill. Very interested to read and take part in the discussions. But going back to the main topic at hand, as noted, in many cases, if there is irreparable damage to your DNA in a cell, this may trigger the cell to either kill itself or trigger senescence, ceasing to replicate. On this latter, there are a number of things that can also trigger this beyond DNA damage, which we'll get into shortly, as it likewise all pertains to why we age. But however it got there, at this point the cell may stick around for a time with a mixed bag of results for you. For example, in this state, while it may on some level continue performing its normal function, it also may not. And further, either way, as Dr. Judith Campisi, who has done some super interesting research into senescent cells we'll get into shortly, notes among many other issues they can cause, they begin to secrete a large number of molecules that have biological activity outside the cell. And that means that these senescent cells can call immune cells to the site where they are. It can cause neighboring cells to fail to function. And it basically causes a situation that is classically termed chronic inflammation. And of course, chronic inflammation is also a great risk for developing age-related cancers. It should also be explicitly pointed out that these neighboring cells that are being damaged can also include stem cells whose function is critical to our bodies continuing to be optimally healthy, but decline as we age, with senescent cells not exactly helping on this front. That said, senescent cells also have benefits in secreting growth factors which help repair wounds. Unfortunately, if a cancer cell is nearby, Dr. Campisi notes, it's possible that the cancer cell will wake up and start to form a tumor. Thus, overall, given their perceived net negative effect, given our current understanding of these cells, much research is currently being done to figure out a way to destroy them while leaving all other cells alone, especially given mice studies show if you remove these cells, the mice actually live as much as 42% longer. On top of that, the mice exhibited much fewer age-related health issues, everything from better organ function than their peers as they aged, to fewer instances of various cancers, and even just visibly looked much younger and healthier than their contemporaries when in their elderly years. Further, they also maintained more youthful propensity for spontaneous activity and exploring, all without seemingly any negative impact on the mice. If you're now curious how they managed this removal in mice and why we can't yet do the same in humans, the aforementioned Dr. Campisi states, it's pretty straightforward and easy to insert DNA into the genome of a mouse and then have that mouse develop into a full-blown adult mouse and have that adult mouse make babies. This transgenic mouse we made carried a piece of DNA that had a foreign protein made when cells become senescent. And that foreign protein had 3 parts: a molecule that was what we call luminescent, meaning we could image the cells in a living animal. It had a fluorescent protein, which meant that we could sort senescent cells from the tissues of that mouse. But most importantly, it had a killer gene, a gene that would normally be totally benign. But if you feed a drug, which is also very benign, that drug and the presence of that foreign gene will cause senescent cells to die. Noteworthy, your body actually clears out senescent cells on its own over time, but as you age, its ability to do this as effectively is also one of the things that diminishes. While even in elderly individuals, these cells only add up to a few percent of your total number of cells at most, it all further accelerates damage and issues as another factor in why we can't have nice biological immortality. Moving on from there to waste products, normally specialized organelles in your cells use digestive enzymes to break down damaged cellular material and ultimately get rid of it. However, over time, this system also breaks down and functions less efficiently, both in its ability to break down these things and get rid of waste from the cell. On this latter point, as cells age, changes to the cell membrane occur, making it both less able to get rid of things and also less able to take in needed oxygen and nutrients. As this happens more and more, the cell will become less effective at doing its job while simultaneously waste will accumulate, causing all manner of issues as previously alluded to. If this builds to a certain point, senescence or cellular suicide will be triggered. As a specific example here, we have protein toxicity. In this one, our cells have their proteins usually kept in a nice, stable condition known as protein homeostasis or proteostasis. To keep things humming along this way, the cell has quite a few mechanisms, including those aforementioned recycling mechanisms for getting rid of damaged proteins. However, once again, as we age, proteostasis declines, resulting in the buildup of misfolded proteins that then, in turn, begin to clump together. This can all cause a number of issues and is integral to many old age-related diseases such as Parkinson's and Alzheimer's. On top of that, over time, the mitochondria in the cell, known for being continually drilled into your brain as the powerhouse of the cell, instead of schools teaching you how to do your taxes, can likewise become damaged and, as this happens, without an optimal powerhouse, the cell function declines, similar to your bank account when the IRS audits you and finds out you've been doing your taxes wrong all this time. Speaking of damage to the cell, there are also countless other things that can cause such, too numerous to list here, but some of the more hyped include free radicals, which for a time kicked off the antioxidant supplement craze, which let's just say research is mixed on such supplements' effectiveness, though when talking antioxidant-rich foods does a lot better. As Harvard Medical notes, one possible reason why many studies on antioxidant supplements do not show a health benefit is because antioxidants tend to work best in combination with other nutrients, plant chemicals, and even other antioxidants. Thus good in theory, but perhaps not in practice. This is somewhat similar to the brief craze that many health issues, including cancer, could be resolved simply by fixing your body's acidity, the so-called alkaline diet fad. In truth, your body keeps a tight lock on its homeostasis in general, and especially on this one, keeping your normal blood pH range at 7.35 to 7.45. Too far out of this range and your cells begin to die. While you might think from this that you really should make sure you're eating things to help keep you in that range, it turns out your body needs no help on this one, and nothing you might normally eat is going to affect the pH of your blood one way or the other, unless you enjoy drinking battery acid. That said, the alkaline diet's recommendation of lots of fruits and vegetables and avoiding alcohol and the like are certainly extremely good for your health, just maybe not working how the advocates of the diet often claim, nor is it really necessary to restrict on certain things as suggested in the diet. But going back to oxidative stress, if these reactive oxygen species are detected in the cell may protect you via ceasing to replicate. Either way, none of these systems protecting your cells and DNA from damage and your body from having the damaged cells replicate or cause issues are perfect. And over time, something of a cascading effect begins to occur from all of it. On that note of cascading effect, let's now talk about the epigenome. In a vastly oversimplified nutshell, this functions as a sort of on-off switch for which genes get expressed or not in a given cell, and can be affected by anything from diet, stress, drugs, to all manner of things that get in your system because you aren't being the person Mr. Rogers knew you could be. On the plus side, the switching genes on and off thing means your epigenome helps your body adjust to the environment it currently finds itself in, as well as adjust for your bad life choices that have made you a terrible disappointment to your mother. However, some changes here can be damaging, and further, as we age, for a variety of reasons, including ones already discussed before with respects to aging, epigenome becomes more and more dysregulated, and noteworthy this also happens even more when more DNA damage is occurring, as enzymes that normally help regulate this are going to repair the DNA. On top of all of this, as our cells and systems decline, our immune responses also do as well, not just affecting our ability to fight off outside diseases, but also the body will become more prone to attacking itself with various autoimmune responses, further damaging various cells and systems. Once again, during this process, and indeed all the processes we've discussed here, this all combines in something of a cascading snowball effect of death, with each of these things generally accelerating the others, resulting in various parts of your body more and more rapidly ceasing to function as well as they once did. Something usually not noticeable at first because your organs and systems are capable of doing their baseline job with vast ability to spare. But as they cease to function as optimally as in your youth, the gap between what they are capable of and what you need to function optimally gradually begins to close, and ultimately, as a result of all of this, one of the horsemen of death will come for you, and at least for now, there's nothing you can do about it. On that cheery note, how about some bonus facts about potentially biological immortal creatures and how we must destroy them for their hubris? First, as demonstrated by the previous Lobster discussion, what constitutes biological immortality can be something of a semantic debate. For example, some consider single-celled organisms that, assuming proper nutrients and environmental conditions, can replicate forever, are biologically immortal. Or for example, a sort of version of this in certain human cancer cells, perhaps most famously in the cancer cells of a woman named Henrietta Lacks, of which there are reportedly millions of metric tons of in labs around the world, used in all manner of research, even going all the way back to being used to help cure polio. Others occasionally posit that we are collectively biologically immortal, descended from a long and unbroken line of cell division going back upwards of a few billion years. And then when talking a bit more complex life forms, similarly there are quite a few clonal plants that are estimated to be in the tens of thousands of years old that some consider to be biologically immortal. But none of that is really what most are talking about when we say biologically immortal, where the original, single, complex life form is able to keep on keeping on potentially forever if they have enough sustenance and some outside factor doesn't come and murder them in their beds like the serial killer that is currently totally not hiding in your closet waiting for you to fall asleep. It turns out though, there are living things that seem like they might fit the bill of this definition of biological immortality, or at least from a practical standpoint. For example, enter the glass sponge, examples of which have been found that are estimated to be over 10,000 years old, but still alive and sponging. Similarly, certain trees, at least from a practical standpoint, seem to be biologically immortal, such as the approximately 5,000-year-old Bristol cone pine tree dubbed Methuselah that's still alive and leafing in California, as it first was when the Stone Age for humans was coming to a close. Of course, with this and many other extremely long-lived tree species, as well as the glass sponge and other such creatures, there is some debate whether they are truly biologically immortal, or it's just that they are so long-lived and mechanisms in place to protect against cellular damage and the like are so good that we just can't observe their slow cellular decline to eventual death. So, at what point does the glass sponge and Bristol cone pine's very apparent cellular and whole body ability to keep on keeping on in their natural environment, if some starfish doesn't come along and nom on them, or with the trees, some human come along and want to build a table, constitute biological immortality? Moving on from there, whenever the topic of biological immortality comes up, the most commonly touted life form is the jellyfish Turritopsis nutricula. This one begins life much like most jellyfish, but has an ability no other creature has. First, the male jelly will release its sperm into the water and it may unite with the egg of a female jelly. Eventually, this will produce free-swimming larvae that leave the body of the female jelly and float around until finally settling on the sea floor and attaching to something sturdy like a rock. It then forms into a stationary polyp that will eventually look like a plant. This polyp feeds on various things like plankton, and over time, a colony of polyps will form from the single polyp, all connected via feeding tubes. At a certain point, sometimes even years later, the colony of polyps will begin to produce free-swimming jellyfish. Now, nothing at all is special so far, and indeed, once they're formed into jellyfish, they float away with the currents, gathering food as they encounter it. The real miracle of this jellyfish, though, is what happens when food is scarce or they are injured or various other environmental cues occur. These events will trigger a unique mechanism within the jellyfish that causes it to begin to grow younger. They continue to grow younger all the way to the point where they once again become a single polyp, starting the process all over again. They will then remain a polyp for a time, even able to grow a new colony. Once again, at a certain point, free-floating jellyfish form and are released from the polyp colony, each with the same genetic code as the original jellyfish that formed the polyp. Their rather unique ability on this front to go all Benjamin Button and, at least as science is aware of at this stage, ability to do this forever has many claiming this creature is biologically immortal. Of course, once again, this all comes partially down to semantics, and with this one, much research still needs done. For example, these creatures, like any other, are susceptible to DNA damage that is irreversible. That said, they seem to have a lot more duplicated genes and vastly more robust DNA repair mechanisms than us lowly humans, allowing them to be much more resilient to such damage. And their ability to revert to their younger selves also is a neat trick that aids all this process and resilience as well. Thus, if any creature is to be called biologically immortal, most go with this one, despite that it would never make any list for the oldest known creatures for various reasons, such as being a jellyfish doesn't exactly put you at the top of the food chain. As a specific example here, we have a specific example here, as a specific In a nutshell, telomeres prevent